As AI models grow, they get smarter, but also far more expensive because every input runs through every parameter. Mixture of experts breaks that link, growing a model's capacity enormously while keeping the work done by input small. In an ordinary dense network, every token is pushed through the entire feed-forward layer, all of the parameters, every single time. So if you want more capacity, you add parameters, and the compute cost climbs right along with them. Capacity and cost are chained together. Mixture of experts unchains them. Instead of one giant feed-forward block, it uses many smaller expert subnetworks side by side. The crucial trick is this: for any given token, only a few of those experts will ever actually run. How does the model choose? A small, fast gating network looks at the incoming token and assigns a score to every expert, essentially a quick judgment of which experts are most relevant to this particular input. It's lightweight, so the routing decision itself costs very little. From those scores, we keep only top K highest ranked experts. In this example, the top two. Every other expert simply stays asleep. So even if the model contains dozens or hundreds of experts in total, only a small handful actually wake up to handle any single token. That selectivity is the whole point. The chosen experts then process the token in parallel, while every other expert does nothing at all. Zero compute spent on them. This is called conditional computation. The model decides, token by token, which parts of itself are worth switching on. Now we have two expert outputs. They are merged into one, weighted by their gate scores. Here, roughly 0.31 times expert 2's output plus 0.28 times expert 4's output after renormalizing those weights to sum to 1. That single combined vector is the layer's result, and it flows on to the next layer. And here is the real payoff. The total number of parameters, the model's capacity, all the knowledge it can hold can be enormous because you're free to keep adding experts. But the active parameters per token, the actual compute, stay small because you only ever run k of them. Capacity and compute are now decoupled. Where does this fit? In a transformer, mixture of experts usually replaces just the feed-forward layer. The attention stays dense and unchanged. Only the feed-forward block becomes a gate plus a bank of experts. Stack many such layers, and the parameter count balloons while compute barely moves. A concrete example: Mixtral. It uses 8 experts in each layer and routes every token to 2 of them. That adds up to roughly 47 billion parameters of total capacity. But only about 13 billion are active for any given token, putting its running cost close to a much smaller model. All of this is learned during training, where the gate is trained jointly with the experts. Because of the conditional computation, only the experts that a token actually used receive gradient updates. So the router and the experts co-adapt over time, each one shaping how the other develops. But there's a catch. Left to its own devices, the gate tends to play favorites. A few popular experts end up doing almost all the work, while the others sit idle and never improve. To prevent this collapse, training adds a load balancing loss that rewards spreading tokens evenly. So every expert pulls its weight. And once routing is balanced, something useful happens. The experts begin to specialize. One drifts towards code, another toward math, another toward dialogue. The model ends up holding far more sophisticated knowledge than a dense network of the same compute budget ever could. None of this is free. Experts are often spread across many devices, so routing them adds real communication cost. The systems are harder to train, tune, and debug, and everything depends on the gate. If its routing decisions are poor, performance quietly suffers. So that's mixture of experts. Many experts, smart routing, and sparse activation. Far more knowledge for much less compute per token. It's how models like Mixtral, DBRX, GLAM, DeepSeek, and Switch reach frontier scale, and it's a key enabler of the next generation of AI. Thank you.